Okay, so we are doing our video presentation on chapter 7.1, which is integral as a net change. By this point in calculus, you should know how to find area under the curve using the Riemann sums like LREM, MREM, and RREM. You should also know how to calculate derivatives and derivatives and basic properties of integrals. In chapter 7.1, you will learn how to use integrals to find net change, such as the change in velocity, total distance traveled, and displacement.
Okay, so some example problems that we have are something like this. So, for the first one we have, the question is, a particle travels with velocity vt is equal to t minus 2 sine t meters per second for the interval of 0 to 4 seconds. Part A asks, what is the particle's displacement? So right here, we set up an integral function, a definite integral function, with the intervals being 0 at the bottom and 4 at the top, and then we write out just what we gathered from our first equation, plug that into the calculator, and we find this answer. And then for part B, it says, what is the total distance traveled? With that, we simply just do the same thing, but in this case, we have the absolute value function. So we have the two lines so that we make sure it's positive. We plug that into the calculator, it's going to be 0.139. Now, for our second example, we have this. And it reads, the volume of a spherical hot balloon expands as the air inside the balloon is heated. The radius of the balloon in feet is modeled by a twice differentiable function r of time t, where t is measured in minutes for 0 to 12 seconds. The graph of r is concave down. The table above gives selected values of the rate of change, derivative RT, of the radius of the balloon over the time interval 0 to 12 seconds. The radius of the balloon is 30 feet when t is equal to 5. Note that the volume of a sphere of radius r is given v is equal to 4/3 pi r cubed. Part A asks, estimate the radius of the balloon when t is equal to 5.4. Using the tangent line approximation at t is equal to 5, is your estimated greater than or less than true value? Give a reason for your answer. So here, we know that the slope is going to be equal to 2. But we are also given the points that when t is equal to 5, here, then the balloon will be expanded to the radius of 30. So that's our points. So we plug that into a simple x, y linear function. And then we plug in our 5 to find b. And then that gives us b is 20. Then here we have the same function, but this time we just plug in the 5.4 because that's what we're looking for initially. I mean, we're looking for the radius of the y there initially. That's going to be 30.8. For B, we find the rate of change of the volume of the balloon with respect to time with t is equal to 5. Indicate units of measurement. So here we use the equation that we were given. V is equal to 4/3 pi r cubed. And we take the antiderivative of that. And then after that we plug in the t is equal to 30. And then that gives us 7,200 pi. Then for C, it says, use the Riemann sum with the 5 subintervals indicated by the data in the table to approximate integral 0 to 12 derivative RT dt. Use correct units, expand the meaning of integral 0 to 12 r derivative RT dt in terms of the radius of the balloon. So here we get the information from our data table, and we just plug in however many numbers of them that there are. We got 19.3 feet from the initial position. And then for D, it says, is your approximation in part C greater than or less than 0 to 12, r derivative rt dt. Give a reason for your answer. We said less than because it is an under evaluation of the area under the curve.
So now we'll get into the common misconception, a thing that a lot of people get confused on. So our common misconception is that displacement and total distance are the same thing, because in reality they actually aren't. So if I were to draw a graph, and let's just say the graph looks something like this. So my displacement technically would be 0, because from start to finish, I end up at the same point over an even interval. So if this was -2 and this was 2, I ended up at the same point over an even distance, meaning that technically I either arrived at the same place that I started or essentially went nowhere. Total distance, however, would be however many feet or miles or whatever unit of measure that I went over the course of this travel. So if I were to set this up in an equation, looking at the problem from earlier, to find the displacement, it's a simple integral function with the velocity function, dt, from whatever to whatever. And when you plug that in, that's the answer that you'll get. But if I were to want to find the total distance, that is when I have to incorporate the absolute value. So everything would be put into absolute value, the entire function. So put in the entire function in the absolute value function, make sure that it remains positive, and this will give you the total distance. So take this function in the parentheses. You're still gonna do all of the integral things, so don't remember your integrals. But when you're finding total distance, it's the absolute value, not just the regular function.